So we have a question that gives us a diagram with two vectors u here and v here. They both start from the origin O, and it wants us to draw on the same diagram two vectors, and the two vectors are half u plus half v, and the other vector is u minus u dot v hat times v hat. Okay, so just a note in the notation, right? We have v hat here, but v hat is just a unit vector in the direction of v, and we can easily express that as 1 over the length of v times v. So this double bar here is just denoting the length of v. Okay. So the first vector, half u plus half v, is easy enough to draw because we just need to note that half u plus half v is just half times u plus v, right? So what actually we need to draw is half times u plus v. U plus v is easy to draw because by the parallelogram rule, we know the addition of vectors is just you follow the direction of u, then you go in the direction of v, right? So we go in the direction of u here, and then we go into the direction of v, will end up somewhere here, right? So I can just draw in the dotted lines to give us the parallelogram. And then u plus v would be from here to here, but what we want is half of that, right? So half of that is just the midpoint of this line, and the midpoint of the line we can easily find by drawing in the diagonals of the parallelogram, okay? And then wherever the diagonals intersect will be the midpoint, okay? And that means that actually this here is the midpoint, right? And that must mean that this vector here from O to this point is half u plus half v. Okay. The second vector is a little bit harder to figure out, so because it's a bit more complex. But what I encourage you to do is think about it component wise, so vector by vector. This is u, right? So if we went from origin to u, we end up here, correct? And then the next term is to minus something times v hat, right? But v hat is just in the direction of v, right? So actually, ultimately, it's something. This is a scalar, something times v. So basically, what we are doing is we are going from u first, and then we are going like somewhere in the direction of v, right? Which means that we are actually going somewhere along this line that I'm going to draw here. I'll draw it in red. Right, so we will end up somewhere on this red line, right? Because this red line is parallel to v, by the way. Correct? And where exactly on that red line we end up, right, is not that easy to tell, but let me give you a hint. This vector here, okay, is actually perpendicular or orthogonal to v. And why is that so? I can give you some time to think by yourself. You can pause the video if you want. Otherwise, I'll show you. And why is this orthogonal to v, right? It's because, okay, we take this vector, oh yeah, let me just write it out. So this vector here is perpendicular to v, or orthogonal. These two words are interchangeable because their dot product is 0. In fact, we learned before that two vectors are orthogonal if and only if their dot product is 0, right? So if we take the dot product of this vector and v, okay, we should get 0, right? So let's just work it out. Firstly, note that we can take out we can distribute the dot product inside. So u dot v and this dot v, right? We can take it out. So this is u dot v minus minus u dot v hat times v hat, and then this thing dot v, right? Okay, and just remember that this is a scalar. a constant. It's constant, it's not a vector. So we can always factorize it out of a dot product. So we can get u dot v minus u dot v hat times v hat dot v, right? We factorized it all the way out so that we are only left with v hat dot v. So now, what we need to do is notice that this is 1 over the length of v times v, right? And this is also 1 over the length of v times v, right? Okay, so actually we can factorize the 1 over length of v's out, and we will get u dot v minus 1 over length of v squared, squared because we have 2 of these v hats, and then we have u dot v dot v. Okay, just notice that we remove the hats by factorizing out the 1 over length of v's here, and we have 2 of them, so it's 1 over length of v squared. And what we can see now, right, is that this v dot v, right, v dot v is actually the length of v squared. Okay, this one is just a theorem from the lecture notes, but now if you don't believe me, you can always just note that v dot v, right, by the definition of dot product, this is length of v times length of v times cosine theta, where theta is the angle between the two angles, right, the two vectors, sorry. And obviously the angle between two identical vectors v and v is 0, right? So this is 1, right? Correct. Cosine 0 is 1. So v dot v is really just length of v times length of v, which is length of v squared, right? And then this, if this is the length of v, right, squared, and then this is 1 over the length of v squared, we can just cancel them away. So this and this will cancel away, and what we are left with, right, is actually just, well, u dot v minus this, right, u dot v. That's all we are left with, and that's obviously 0. Okay, whatever u and v is. So now now that we have found out that this vector is perpendicular to v, right, what that means is that actually this vector must lie on this line, right? Because this line is perpendicular to v. V is here, right? So this line must be perpendicular to v. So it's somewhere here, right? I'll draw it as a blue line, right? So this vector number 2 must lie somewhere on this blue line. But then just now we already concluded that the vector must lie somewhere on the red line also, right? Because it's u minus something times v. And since there is only one point that satisfies these two properties, there's only one point that lies on this red line and the blue line. Obviously, it's this point, right? You can see quite clearly. Then this must be the vector that we need to draw, whatever this vector is. And so we just need to draw the vector like that, right? And this we label it as u minus u dot v hat times v hat.